One of my favorite things about chemistry is how well it connects with the everyday world. And one of the things that I will end up saying a lot, or one of the basic principles to that, I suppose, is this idea that structure determines properties, that how something behaves is entirely dependent upon how it's put together. So the molecular structure determines the properties. We've seen some of that in terms of intermolecular forces with boiling points and solubilities, but we're going to see it apply in a much more realistic way, or in a much more everyday way in this video. So if we take a look at some of the things that we know where we can actually start to talk about chemistry for this. Oil and water don't mix, and that's something that's been known for a long time. You probably, long before you ever took any science, maybe you learned about that oil floats on water. And if you shake it up, what'll happen is you'll get these oil droplets dispersed through the water, and the more you shake it, the smaller the drops will be, but they will eventually resettle out so that those droplets gather together. On the other hand, if you put oil on top of water in a large area, that oil is going to spread out over that area, and you're going to get this rainbow. It's still not really going to mix that well. So in terms of solubilities, water and oil are not soluble in each other. And if we talk about the structure of oil, so here I've got a molecule of, this is actually going to be more of a vegetable oil or a fatty acid rather than like a motor oil. But we have a lot of non-polar bonds in there. We've got carbon bonded to carbon. We also have some carbon bonded to hydrogen, and those, if you look at the electronegativities, are going to be fairly non-polar. There's also going to be a fair bit of symmetry within the molecule, not a lot, like not 100% symmetry, but there's going to be areas of symmetry where we're going to have a non-polar area of the molecule. Yes, way down on that end we do have a polar end, but it's not going to be significant enough to mix well with water, because water has very highly polar hydrogen-oxygen bonds. It's capable of doing hydrogen bonding with that, and there is a couple of areas on that large oil molecule that could, but there's so much in the oil molecule that can't. If I add a little soap, and that's the thing that we use in dishes, in laundry, in showers, even in, well, not so much in food, but we will add something that we can then turn that oil and water mixture into an emulsion. If you were making something like a mayonnaise, if you're making something like a salad dressing where we want to emulsify the oil throughout the vinegar is really water-based, then they'll add something else. Mayonnaise, one of the classic ones there, is to add egg yolks. So if we add a little soap, then we will turn our oil-water mixture into an emulsion. They're still not dissolved, but they will actually mix together. And the reason for that is if I look at a molecule of soap, and if you took a Pioneer unit way back in the day, with making soap, they start out with using fat. Or you can get vegetable oil soap nowadays, but they'll take a fatty acid, long molecule of oil that we had, and then they will mix it with something, potash or lye in some cases, and they will make that one end ionic. And an ionic compound mixes better with water. So what you end up have happening is the soap particles will form what's called a micelle. And a micelle is just all of those soap molecules trying to do the oil and water thing. So the part of the soap molecule that mixes well with water will face outward, and the part of the soap molecule that is nonpolar will face inward, and you end up with something that looks a little bit like a koosh ball. And then the oil that's in your clothes or on your body or in your dishes, that is going to get drawn into the middle, where the oil molecule mixes with the nonpolar oil molecule mixes with the nonpolar part of the soap molecule, and then the water of your solvent surrounds the ionic part of the soap molecule, and then the oil was able to wash away and get rinsed away. So that's basically just what I got finished saying. You may have come across the terms hydrophilic and hydrophobic, but I'm going to move on because I'm talking too much. Sugar dissolves in water. We know that. Some people put way too much sugar in their tea or coffee. But sugar has, if you were to look at the molecular structure, it has a lot of carbon-carbon bonds, but also the outside, there's a lot of carbon bonded to oxygen and oxygen bonded to hydrogen pieces on that. So what you have is, I'm going to go back one, a lot of places where water can interact with the sugar molecule, thereby dissolving it. Nail polish is really interesting stuff because when you put it on, once it's on, I shouldn't be pointing to my nails, I guess, but when you put it on, it's pretty durable. You can wash your hands, you can wash the dishes, you can wash your car, and it's not going to wash off. And I came across this, I don't know if it works, but there you go, a little tip of the day. But if you decide you don't like the color anymore, it's really easy to wipe it off. A little bit of nail polish remover on a swab, and away we go. And it comes off really, really easily. So in some solvents, like water, it doesn't mix. But in other solvents, it does mix and does dissolve. Every once in a while, you'll pick up a bottle that has oil in it. And the bottle, even if it's never been opened, will have a bit of an oily feel on the outside, as if the oil is seeping through the plastics. And really, it is. And the reason for it is a lot of those plastics, which in many cases are made from oil-based products, have a lot of the same kinds of molecules, same kinds of bonds, same kinds of polarity as the contents of the bottle. So the oil in the bottle does start to seep through the oil of the bottle or the plastic of the bottle. So you'll sometimes get that oily feeling. Okay, so a lot of plastics, or some plastics, or really common plastics, actually have that structure behind me, and then the oil one is that we saw a little while ago. I came across this article, it's a few years old, but the fact that certain plastics absorb certain contents makes those bottles very difficult, if not impossible, to recycle. Not because you couldn't recycle, just because you don't want the residue of the contents. So being able to find a way to remove the contents that have seeped into the bottle, that actually becomes a really important thing. I don't want to make you think that your cotton socks are trying to kill you in your sleep, but for certain people who are hiking in certain areas, you will sometimes use that phrase, or I've even seen it on a sign in a couple of different places, because if you are out hiking and you're kind of far away from help, and you get wet or your clothes get wet, cotton is going to stay wet for a long time, and that puts you at a bit of a risk for hypothermia. So wet cotton stays wet, and the reason is, or some of the other dangers to it, is that it loses insulation, it doesn't wick moisture away, you stay wet, all the moisture stays on top of you, and it does take a long time to dry. The reason for it is cotton is sometimes considered to be it's a long chain of sugar. It's a polysaccharide. So you have a lot of areas on the particle on the cotton molecule where water can interact. It's not going to dissolve the cotton, which is good if you do get wet. You wouldn't want to put your clothes in the laundry and they come out nothing. But it does mean that the cotton is going to hold on to that water. And labels are important. You can ignore all the spelling mistakes on this label, but on that label, one of the things it says is cold wash separately. And if you took a brand new towel and dumped it in the wash, then everything, all that cotton, all that dye starts coming out, but only on certain things. Cotton-based materials need a dye, a colorant that holds on to cotton particles. Well, whatever holds on to cotton particles is also going to mix well with water. So your cotton stuff tends to fade quite quickly in the wash, and a lot of that colorant will come out in the first couple of washes, and all your white socks turn whatever color your cotton towel was. And that's simply because structure determines properties. If you want that colorant, that dye, to stick to cotton, it's also going to naturally mix well with water. Graffiti remover isn't going to be water-based because graffiti, paint, wax, things like that aren't going to be water-based either. So I found a can of graffiti remover, and the label says it's going to remove paint, crayon, marker, ink. You can read those as well as I can. But if you think particularly about wax and crayons and things like that, lipstick, those are very, very waxy. They're oil-based. So your graffiti remover is going to need to be oil-based. And I looked at the data sheet on this stuff, and it said it contained toluene, isobutane, and xylene. And not that we care that much, but if you were to look at the structures of those things, toluene, isobutane, and xylene. those have a lot of carbon-carbon bonds and a lot of carbon-hydrogen bonds, and we know from earlier that those are low polarity or non-polar. So those are going to be fairly low polarity molecules. So if wax is a low polarity molecule, toluene isobutene and and xylene are low polarity molecules. Likes mix with likes. Decaffeinated coffee, why would you ever? But if you did, caffeine is going to be a molecule that has fairly low polarity. It does dissolve in water, not that great, but it does dissolve a little bit in water because that's how we get caffeine in our coffee. It dissolves better in low polarity solvents like benzene and dichloromethane. Here's the problem with benzene and dichloromethane is they're really, really bad for you. Now the upside is if you were to use that stuff to decaffeinate your coffee, no problem, you could, I shouldn't say no problem, but low problem, you could, once you rinse the solvent with the caffeine away from your coffee beans, you could evaporate the rest of it out, leaving very, very little amounts of residue. However, people don't want the amounts of residue, so that method of decaffeinating coffee isn't so common anymore. Caffeine and some of the other solvents that they are using to do that. Okay, I could go on. I'm trying to keep a lid on the time, but there is the answer, or sorry, not the answer. There is the real question that we need to ask ourselves every day. Talk to you another time.